So we ended the last class with this example. How many moles of neon gas occupy 2.34 liters at STP? So what this was referencing, or what one way we could go through and solve it, was using that really silly equality that I said that is a bad idea, but it at least exists and is true, so we could theoretically use it. 22.4 liters equals 1 mole, okay, which works for any gas. The way that I went through and showed it was using PIVNR, PV equals nRT. When we go through and rearrange that to solve for moles, it'd be moles times volume times P over RT. And if we solve for P over RT, we get 22.4 liters equals 1 mole. So the conversion factor of 22.4 liters equaling 1 mole comes from PIVNR. Okay? That is why I would argue that you shouldn't be using the that PIVNR is powerful and you should use PIVNR because it has that information. The reason why the 22.4 liters equals 1 mole is a bad idea is that you see that and you try and use it in all circumstances. There are massive exceptions to it. It only works for gases. It only works at standard temperature. It only works at standard pressure. All of those conditions combined means that most of the time that you encounter in larger chemistry courses, conversions between moles and liters, you aren't using that, right? And that's where it becomes problematic, or you can't use it. It is now a false statement. That's why PIVNR comes in handy. It's set up as this kind of its own unique thing, which means if you think you're working with a gas, you immediately jump into PIVNR, and now you don't worry about necessarily using molarity or getting confused with other things. PIVNR already locks you in on the gas side of things. You can make the substitution for your standard temperature, make your substitution for the standard pressure into the equation. You don't have to memorize an equality that doesn't work most of the time. Okay? So that's my argument for PIVNR. For this class, you could probably get away with memorizing 22.4 liters equals 1 mole with one big exception. It has to be for gases. Okay? That's our rule for the final. For the next exam on Tuesday, we have to remember not only is it true for only for gases, but those gases must be at standard temperature and pressure. Okay? That is such an important distinction that you will see questions where STP is written in. And you might trigger and go, oh, well, I can use 22.4 liters equals 1 mole. Right? It won't be, because it won't be a gas. Okay? So don't just immediately jump to that conversion because of STP. It is only true for gases and STP. Both of those conditions must be met. If they aren't met, you can't use it. Okay? So what do I really want? Your responsibilities is 22.4 liters equals 1 mole for gases at STP, and then recognize the utility of PIVNR. Okay? It allows you to see the relationship between volume and temperature, pressure and volume, pressure and moles, all that fun stuff, so that you could do numerical relationships and come up with those numerical answers relatively quickly and easily. Okay? If you choose to not use it, that's fine. That's your choice. Okay? You're cool. The next one is Dalton's law of partial pressures. Okay? One of our assumptions was that each of our gases was not distinguishable from any other gas. That means if I change the identity of the gas, it doesn't matter. It has no effect. Okay? As long as there's a gas particle, it's occupying no volume, so the volume doesn't change. Since it doesn't interact with other particles, it doesn't interact with other particles, so even if I change the gas, it doesn't matter. All I care about, is there a gas present? Okay? So if I go through and look at a system that has a bunch of different things, what I could go through and do is just say, well, what is the pressure of each of those parts? Add all of those parts together, and I now have the total pressure. Okay? And this is because it is an ideal gas. Okay? So the example, if I take a sample of gases with those pressures, how would I determine the total pressure? Yeah, add them all up. That's literally it. Okay? Millimeters of mercury, is that the pressure unit that we're supposed to be using? We talked about it a lot, but no, atmospheres was our standard unit for pressure. So does that mean you need to convert to pressure or atmospheres? No. Why not? It doesn't say so, number one, so it's a bad question. It should specify the units that we want for our answer. And number two, what did I say about converting pressure units? You don't have to do it. That was literally what I said. Don't do it. Okay? So all you have to do is add all those numbers up. Should we actually do the math on that? No. Okay. The next concept that comes out of our gas law chapter ties back to kelvins. Okay? Temperature was a measure of energy, Kelvin being the absolute temperature. One of the things that we could go through and do is track what happens with temperature and energy. Okay? Kelvin does not drop below zero. Okay? At zero, we're saying there is now no energy. So zero is our absolute lowest. Okay? That simplifies our calculations. Because we now have an absolute zero, we can reference it as absolute zero. So you might have heard of absolute zero before, outside of the context of the class, because that's kind of a weird concept. If we hit absolute zero, what does that mean to the energy of all particles? There is no energy. Well, if there is no energy, is there motion? No, because motion is energy. Right? So it's kind of a bizarre concept to kind of wrap the brain around. Right? Everybody's been trying to achieve absolute zero, right? Because that would be a neat thing to do. And there are scientists that have created experiments that generate temperatures that would theoretically be less than 0 Kelvin. Okay? So let's take a second to process that. Absolute zero is our absolute lowest, which means no motion. We don't have negative temperatures, and yet somebody created a system in which the only way that system would be true is if we were at negative kelvins.
Can you have negative motion?
And it's not, kind of, yeah. Okay. It is a really kind of mathematically complex system, okay, that gets at other rules of thermodynamics, so the study of temperature or the study of heat. Okay. If you're interested in that, you can talk to me after class and we'll try and look up the paper and see if we can discuss what's going on with it. There's some other things that are beyond the scope of the class. Okay. It could also be something that if you take more chemistry classes, you could throw it at the instructor and be like, well, I heard they obtained, I believe it was -4 Kelvin. Okay. And the instructor will say, oh, absolutely not. And we'll do some research and you can probably find the paper that says we actually obtained -4 Kelvin. Okay. What's that?
Did they get to like a millionth of a Kelvin?
They got, all I know is lower than 0. Oh, otherwise in other experiments, they've gotten really, really, really close to 0 from the positive end. Okay. The negative end, because that's the other weird thing, is they never passed through absolute 0. Yeah. It's when you get into the quantum realm, all sorts of weird stuff happens. Okay. So we don't pass through 0 to obtain the system, but this system has been created, at least temporarily, which then suggests that negative kelvins are possible. Okay. Or would need to be possible for it to be true. Okay. Which could just mean that our equations to represent the phenomenon that we're observing are incomplete, and we're missing a small piece. Okay? So, absolute 0, 0 Kelvin. Okay? Are you responsible for converting Kelvin in degrees Celsius? Yes. Are you responsible for converting degrees Celsius into Fahrenheit? Yes, which means I could say 0 Kelvin, or I could say -273 degrees Celsius. Or negative whatever the heck that conversion is through Fahrenheit to get over into Fahrenheit. Okay, you're responsible for being able to do those conversions. Remember, one of those conversion factors is found on the exam. Okay? Which gets us now doubling all the way back to chapter 9 and a fun little concept where we can deal with our conversion factors again. Okay, the limiting reactant concept. Okay, we've got a recipe up on the board. Okay? 1 slice of cheese plus 2 slices of bread make 1 sandwich. Admittedly a boring sandwich, but it's a sandwich. Okay? if I give you 5 slices of cheese and 8 slices of bread, how many sandwiches can you make? That was a really fast answer. Okay. And is it correct? Yeah, okay, cool. So we're going to take a moment here and say, okay, that was a phenomenal job. I absolutely agree. Hats off, fantastic. 2 moles of sodium carbonate are mixed with 2 moles of water, 1 mole of carbon dioxide. How many moles of sodium hydrogen carbonate are produced? And answer. Okay. Becomes a little bit harder to process. Some people were able to come up with that math relatively quickly. Okay. If you weren't able to pick it out with this, but were able to pick it out over here, it's because in this situation you've dealt with it. You've seen these physical objects. You can manipulate those symbols better than you can over here. But the rules that you should be following to figure out how many sandwiches you get versus how much sodium hydrogen carbonate you get are identical. There is no difference. So what is the process that you need to do to determine how many sandwiches you can make? Conversions. Elaborate. Okay? Fair enough. You've provided our first step. You don't have to elaborate. Somebody else elaborate. We're doing a conversion. Okay, unit conversion. Put it this way, the longer you don't come up with a suggestion, the harder your steps are going to become.
Slices of cheese and slices of bread, 2 sandwiches.
Right? So that's a pretty huge one that you provided. That's actually going to take me a little bit of time to start writing stuff out. Okay, that's okay. It's good. You're actually being nice to everybody else. Okay, because you said to convert to sandwiches, slices of cheese. I'm not writing slices. I'm going to say cheese into and bread into sandwiches. Okay? Cool. We're moving somewhere.
It's like a piecewise function.
Okay, now what? Heard something about taking the slices of cheese and turning it into sandwiches and the slices of bread and turning it into sandwiches. That is exactly what was just suggested, and I've just translated that information. Okay? I don't see a ratio written in there. Are you suggesting I should use a ratio? I should make one. Where do I want to place said ratio?
Well, I wouldn't do 2 separate equations, but I would go into 2 separate equations. That's not how.
Okay? So you generate a ratio for me for just the red one then, and we'll ignore the purple one. Okay? So I want to see your ratio that allows me to solve without doing a second conversion. So what's your ratio? What's that? 1 cheese over 2 bread. It's a step. Is that a useful step? Why are you shaking your head? I like it.
Because red's a different equation. So it could be like 1 cheese.
Okay, well, the argument was made, and while I may agree with you, the argument was made that I don't need a separate equation. Okay? So we can't quite go through and say, well, bread's a separate equation, so we can't use it. Because the argument's being made that we don't need a second equation. Okay? So what else might be an objection that you got to that?
You would also need like the amount of bread that you have at the beginning.
Okay, so I would need the amount of bread that I have. So where do I want to put the bread that I have? In the bread equation, which is now going to be a problem because that's a second expression. The suggestion was made that I don't need a second expression. Everybody else is now saying that we do need a second expression. So, Molly, you wanted to try and defend that I can do it all in one step.
Yeah, I think we did it all in one line.
Okay, where do I want to put in the information about the bread that I've got?
Well, could you switch it to 2 bread over 1 cheese instead? So we can cancel out the cheese.
Okay, so let's pause for a second. Now there's a suggestion being made that cheese over bread was a horrible conversion factor. Why is that conversion factor not useful? What does this do to the units? It does not cancel out. Okay? At best, we're now getting cheese times cheese, so cheese squared divided by bread somehow equals sandwiches. That doesn't quite work. Okay, so let's run with that and say, okay, that conversion factor was placed incorrectly. 2 bread, 1 cheese. So we've now converted cheese into bread. So what's your next conversion factor? Do we have sandwiches yet? No. Okay, so we're seeing some thoughts and kickings over here. What's our thoughts and kickings? What are you suggesting?
I'm humble and lost, so.
Meat?
Oh, no, it said me.
Oh, okay. I was like, don't make it worse. We don't need to add meat to our sandwich.
I would have changed the conversions.
You would have changed the conversion.
Yeah, like something like wheels of cheese going into a slice of cheeses, then over.
Okay, do we see anything that where our cheese is coming from? Like, do we need to slice it? No, this actually says it's sliced cheese, so don't bring in wheels of cheese. Okay, that's like bringing in meat. Meat's not relevant to the question. Wheels of cheese aren't relevant to the question either.
So could we do like 2 slices of bread makes 1 sandwich? And so we can just do,
Okay, so what you're saying is, I don't know what's going on with doing this all in one step. So let's shift focus and just look at the bread.
no,
And
let's
say-
in the top side.
Oh, okay.
Get rid of the bread and turn it into sandwiches.
So 2 slices of bread equals 1 sandwich. You want to put it up top.
Yes.
Okay. What would happen with your units?
The cheese would cancel out and the bread would cancel out and you would have a sandwich.
You would have sandwiches. So what is our numerical answer?
1.
Didn't we say the numerical answer was 4?
I tried it another way, I got like 1 and a quarter.
What are we missing?
The bread and the cheese.
2 slices of bread.
There's no slice of
We're
cheese.
missing 2 slices.
Say that again, Alex.
The cheese and bread were given, the 5 slices.
We have 5 slices of cheese. What's out in front here? I didn't write anything. Why? You didn't tell me to write anything. How much cheese did you start with? 5 slices of cheese.
Still get 10.
5 slices of cheese times 2 slices of bread, cheese. So cool, I'm canceling cheese, canceling bread, and I would get sandwiches, and I would get 5 sandwiches, which was also not what we said the answer was.
You just add the given bread.
You're put 8 bread over 5 cheese.
Okay. 8 bread over 5 cheese. 8 bread over 5 cheese is not a conversion factor. That's just taking all the information I've got and putting it all together, saying if I have 8 slices of cheese and 5 slices of bread, I'm just going to jam all that stuff together and ta-da, I get sandwiches. There's no ta-da when we do anything. Is converting it to bread useful at all? What happened to our bread conversion?
It canceled.
It canceled. Is doing a bread conversion useful? Okay, you're shaking your head. Why are you shaking your head no?
Because, like, even though it takes 2 bread to have a sandwich, it also takes 1 cheese as well. So you can just do 1 sandwich over 1 cheese.
So to solve this, I'm going to multiply this side by 2 and this side by 2. Was that useful to solve this? You're right, because it wouldn't do anything, right? Okay, so I'm going to divide this side by 8 while multiplying by 2, and still multiply that side by 2 and divide by 8. Would I now solve the question? I would get x equals 4y. I would know what x is. X is 4y. Did I need to multiply by 2? No. Why not?
Could have divided by 4.
I could have divided by 4. Did I have to do that extra step? No. Why? Because I repeated it. When you converted to bread, what did you then do? You canceled out the bread. So you said, I'm going to convert to bread so that I can get rid of bread. I'm going to multiply by 2 so that I can...
You added sandwich into that also by converting to bread.
Okay. So maybe I needed to add the sandwich in to convert. So I can only convert bread into sandwiches. Can't do cheese into sandwiches. Where did you get 1 to 2? Sandwich to bread. From the balanced chemical equation. And that balanced chemical equation says nothing about cheese, right? Oh, it does say cheese. You mean, couldn't I have just said 1 cheese equals 1 sandwich?
Subject to the same answer, it's not good.
Cheese cancels, I get sandwiches. You added an extra conversion. Why did you add the extra conversion? Oh, because there was bread. Are bread and cheese the same thing? No. Can I convert both bread and cheese to sandwiches at the same time? No. Which means, what do I need? 2 equations, where I will convert cheese into sandwiches, which gets me 5 sandwiches. And yes, we might say that that was the wrong answer. But why was it the wrong answer? Christian, you came up with the answer and said 4 sandwiches. Did you look at the cheese to determine that you got 4 sandwiches?
Yeah.
So somehow 5 cheese got you...
Yeah, when I did the ratio in my head.
Okay, you got 5 cheese became 4 sandwiches?
No. Or, yeah,
So
I
did you-
technically. I'm so lost on what you're asking.
Okay. The answer was 4 sandwiches, right?
Yeah.
That's it. When we convert cheese into sandwiches, how many sandwiches do we get? 5. How did you get 4 if you looked at the cheese?
Because you only have 8 slices of bread.
Did you look at the cheese?
Yeah.
No, you looked at the bread.
Well, I looked at both.
Yeah, the dictionary.
There we go. 8 slices of bread. When we did the conversion, you aren't looking at a single piece of information, you're looking at
Both.
2 equations, 2 solves. In that, you now have 2 ways to attempt. And in your interpretation, you said 8 slices of bread is not sandwiches. What did you have to do? Convert. How many slices of bread make 1 sandwich? 2 slices of bread, 1 sandwich. What happens to our answer? 4 sandwiches. Why did you not say 5? It's small. Okay, it's smaller. Why? What does that mean? What does it mean? 4 is smaller. Yes, so is 3, yet 3 was not the answer. Why can't I make 5 sandwiches? I don't have enough bread. Okay? This concept you have, but again, you aren't establishing any conversion process. Which means the instant we move to a system that you have no physical control over, you're lost. All I'm asking you to do is write down your process. You mean all those things that Greg's been saying, hey, write down the steps that you take to do this? That is exactly what I'm asking you to do here. And because you've internalized, oh no, it's easy, I can do that. You literally cannot do that. You have no concept of it because you haven't built a process. You've built an algorithm where you can be like, well, I can put a slice of cheese on 2 slices of bread and you can see that. What if those numbers are not 5 slices of cheese and 8 slices of cheese? 5 million slices of cheese, 62,342 slices of bread. Can you manually go through in your head, well, there's 1 slice of cheese to 1 bread, to another bread, next sandwich, next sandwich. Can you do that in your head?
3,000, 31,000.
So, and you're going to argue, oh, I just did. What did you just pull out? A calculator. You can't do it in your head. You can't. You have to write it down. Okay? You're not able to do that. That's the whole point of the writing process. Okay? And when we look at those calculations, it's not a shame. That's awesome. Okay? We now have a proof in point case that you can't do it. Okay? You have to write the work down. That's it. That's the lesson. The last 6 weeks have literally been write it down. Okay? And you might be, well, that's just chemistry. What has Greg been asking you to do for the last 6 weeks? Did you write anything for a draft? You mean, did you write anything down? That's all we've been asking you to do, is to literally write it down. Okay? That action you aren't taking. That action is why your average on the exam is 20 points lower than standalone classes, where they are actually writing it down. That's all this is. Write it down. Yes.
So why can we not solve one line? Like, obviously, explicitly, yes, but if you were to look at a chemistry
He
problem.
did solve it in 1 line, but it was just a different line.
No, he did solve one. It's 2 different.
You can't solve both of these at the same time.
So,
Okay? Why do you need to do it? You have to establish what is the limiting reactant. There's 3 pieces of information. You have to see the relationship between each of those pieces of information. If you can only compare 2 things, Harry's taller than Sally, Sally's shorter than Jimmy, Jimmy's taller than Jerry. Okay? What's the height difference between Sally and Jimmy? I don't even know if I say the same names again. Okay? In those types of problems, in ranking problems, you are never jumping to the answer. You're establishing the relationships. How do you establish the relationship? By looking at 2 things. Okay? If I want to play the 7 degrees of Kevin Bacon, which I'm sure I don't even know if it's Kevin Bacon, whatever. The relationship between any individual in this room, we don't try and go, well, Alex and I are tied. How are we tied? How are we connected? Who does Alex know? Who do I know? How are those pieces connected? We don't immediately jump to the end. The process that you need is this middle part. That process for that middle part is very hard to hold on to in your head. Okay? Up to this point, as far as I can tell, your experience outside of this class has been able to do single steps with very small numbers. Humans are great with small numbers. In fact, we're great with numbers that are less than 10. Why less than 10? And it seems insulting and stupid because we literally have 10 fingers. The instant we move beyond that, we don't understand. Like, that's totally not true. Okay? I would make a very solid argument that we don't understand 12. Like, that's nonsense. We totally understand 12. We don't understand 12 so poorly, we invented a new word to define 12. We're stupid people. We are. This is why we've invented systems to help us process it. If you decide to not use those systems, you are literally sticking yourself on 10 fingers. Okay? I don't want that for you. I really don't. Okay? I want you to expand well beyond that. To expand beyond that, we need new symbols. We need new words. We need new understandings. Okay? That is the point of science, is trying to grasp that stuff that our brain can't deal with. So we invent a word to mimic it. That's what's happening. It is this process. Okay? So that when we switch it up and move to a system that we're like, I can't grab a molecule of sodium carbonate, I can go through and say, well, if I'm trying to make sodium hydrogen carbonate, and I start with sodium carbonate, how do I do that? I can't grab it and say, well, I'm taking a slice of cheese and putting it on between two slices of bread. I don't have that ability anymore. I have to have a system to work with. That system is this dimensional analysis process. Okay? And in this case, it's not just sodium hydrogen carbonate. What am I being asked for? Because it's not just the substance.
Moles of sodium.
I'm being asked for a measurement. What is that measurement? That measurement is moles. So when I set up my equation, I have to include that in here. Why did we invent moles? To better understand or better measure chemistry, because we can't measure it easily when we're looking at single particles. So we invented a new system. Okay? How do I establish this conversion? Well, I'm starting with sodium carbonate. I'm making sodium hydrogen carbonate. How much sodium carbonate did I start with? 2. Content from the question. Okay. Are those substances the same? No. How do you know that? How is Na2CO3 not NaHCO3? They're different symbols. And why you might say, that's stupid. Why are you asking me that? It's not stupid. Right? It is a simple observation that if we don't intentionally make it, we screw it up. We're stupid. We are. Okay? We need to stretch our brains and work at trying to advance forward. And again, notice the use of we. This is not you. This is me. Okay? I'm trying to help you by pointing out my flaws. Because you're being like, well, those aren't my flaws. Look at your exam. They are. Okay? And that hurts. Okay? That really, really hurts me. Okay? So, we look across. We don't see them the same, so we have to establish some kind of conversion. Sodium carbonate needs to be in the denominator. Why do I need that in the denominator? So that those units could cancel. The substance can cancel. What substance do I want? What substance do I want? Sodium hydrogen carbonate. Okay? Yeah, I've got my substance. I'm recognizing that. To establish that, where do I find my conversion factor between substances? Pointing up is a good option, as long as you're pointing to the top of the screen and not outside the building, because up doesn't help us then. The balanced chemical equation. All right, so we would look at the balanced chemical equation and notice the number in front of sodium carbonate is 1. The number in front of sodium hydrogen carbonate is 2. And the answer becomes 4. Some people were really good at internalizing those calculations, and they punch through 3 calculations insanely fast, and my hat is off to you, because that is phenomenal. Okay? But the problem will become less easy numbers. You won't be able to do that math as easily in your head. You need the process. As you continue to go through, since there's 3 starting materials, just like with the sandwich, we needed 2 equations because there were 2 starting materials. 3 starting materials means 3 equations. So we'll set up 3 equations. When we go through all of that work, the second or the last equation in converting CO2.
Is it really that
We'll address that here in a second. Moles, what's our relationship? 2 to 1. This one was 1 mole of CO2, and we get 2 moles sodium hydrogen carbonate. So our answer becomes 2 moles of sodium hydrogen carbonate. You did a phenomenal job. Okay? What I'm going to guess happened to get it that fast is exactly what Nick is trying to ask about. Why do you think I don't have to do the other 2 equations?
Well, I see at the balanced chemical equation, I see it's 1 to 2 for everything on the left side. There's only 1. So I look down at the question that you just erased.
So, pause. Okay. I looked at the chemical equation to establish 1 to 2. You mean you've created a conversion factor? Yes. You've internalized that conversion factor. Then I look down to look at the question so that I could insert this number into said conversion factor so that I could run this calculation in my head. Yes, you can do that. Okay, again, you're doing it in your head. You're doing it 3 times. Because the conversion is simple, you are able to do that conversion 3 times incredibly fast. The instant you can't do it, you don't have a written process. You have no muscle memory to go, oh, this is what I need to do. You're now being like, well, this is what I did in my head. Oh, but I can't do, oh, let me write down those numbers. The instant you're now doing, what did I do in my head, and trying to write it down, what just happened is you increase the odds of making a typo and writing numbers down. The numbers do not hold meaning. It is the units tied to them. And because you're able to internalize those units and hold them, that's cool until the instant you can't do the math. Now your brain has to shift gears. You lose track of the units, and you have no way of recovering how to put the numbers together. That lies in the problem. Continue.
Well, I was just thinking, like, so after analyzing the question, you see that there's only 1 mole of carbon dioxide, and there's 2 moles of the other 2.
Okay. So this, I would argue, happens as well. Students go through and read the question and say, well, there's only 1 mole of carbon dioxide. That's the smallest one. That must be the answer.
Based on that information and the balanced chemical equation.
And the balanced chemical equation. So the instant you're saying, based on this information and the equation, you've done the conversions. These conversions were simple. You were able to do them in your head. Again, by not writing them down, you're shooting yourself in the foot because you don't have the muscle memory for an easy conversion that you know you can get right. Which means when we move to the exam, you don't have the muscle memory to write it down. So instead you go, oh, I have the brain power to pull this off. I'm going to run the calculation. But then your brain screws up. And you write the wrong thing down. You write the wrong numbers next to each other. Okay? The numbers without those units have lost their meaning, and you do the wrong calculation. Okay? If we look at just the question and say 1 mole of carbon dioxide on its own, that also does not work because the chemical equation could significantly alter the output. Okay? Yeah.
So I'm kind of thinking is how much work you need to show on the test in order to get full credit? Do you need to show equations? Or just
So
like
there's an
numbers?
interesting question. Would this question be a show your work question on the test? A majority of people were able to pull this one off in their head. By making it a show your work, what have I done? I penalized those people for being smart at what they do. This would not be a show your work question. This would be a straight up multiple choice. Okay? When does it become show your work? When those calculations cannot easily be done in your head. That's when it becomes show your work. Okay? Because you need to prove the process all the way through it. Another reason why this is not show your work, how many conversions are you doing in each of these? 1. Which means the odds of you getting it right are 50-50. I'm not going to ask a multiple choice in a show your work that's a 50-50 odds of you getting it right. Okay? That doesn't make sense. That doesn't prove anything because you could have lucked into guessing that. If I've stacked 2 conversions after this, the odds of you lucking into showing your work for that drop drastically. Now it makes sense as a show your work. Okay? In a multiple choice, guessing is always an option. So I'm okay with a 50-50 flip happening in that. Every single conversion is a 50-50 unless you have the intent. The intent is what drives this.
On the last exam, how many points were show your work versus Scantron reference?
So it looked to me like on exam 1 that people skipped show your work to move to multiple choice because the multiple choice was worth more. On exam 2, that balanced out a little bit better. The majority is always going to be multiple choice because our final is multiple choice. So it's trying to mimic that. You're looking at roughly 65-35 or 65-40. Okay? Roughly 60%, 60 to 70% of the points will be multiple choice. 30% will be show your work. So as you're saying, well, 70% would be awesome, then you can ignore the show your work, okay? Because you aren't able to show your work. That's okay. Realize if you can't show your work, you're probably guessing on the multiple choice. Your odds of getting 70% or getting all of those 70% right drops, and you're probably now sitting at a 30% on the exam.
And I'd say asking the question of how much work do you want to show is not the question that's most effective. Because if you say, Mike, how much work do you want me to show on a multiple choice, well, it's not how much work he wants you to show, it's how much work you need to show to be able to hang on to that information. If you don't have to show your work on the multiple choice, that doesn't mean that you can solve that problem without doing work and without setting up the problem. But if you can't set up the problem on the multiple choice like this, you're not going to be able to do it on the
Show your work.
Handwritten, on the, what are they called?
Just show your work. That's
Show
right.
your work, yeah. So as a writer, you write stuff down to hang on to the information so that your brain doesn't have to. I used to have to do calculations all the time when I worked at the block yard. I would have to deal with inches and cubic inches, cubic feet, that kind of thing. One time I got bored while driving, and to help myself stay awake, I converted how many cubic inches are in a cubic yard, just to mess with it. It took me 10 minutes. If I sat down, because I couldn't write stuff down, if I sat down and wrote that down, it'd take me 10 seconds because I knew the math and the conversions and all that really quickly. But because I could write it down, I would be able to hang on to that information differently, and my cognitive processing would not take as long. And so, even on simple questions, as a writer, it's going to benefit you cognitively to write stuff down and lay some of this out, and then you can go back and check your work because you've encoded information that you can come back and confirm or reject. If you don't have enough work written, you can't confirm or reject it even on a simple problem, so you don't know if you're doing it right in your head or not.
I've seen everybody's work. Everybody has work that will satisfy everything on the exam. The issue is not writing it down. That's it. Okay? That's really it. You just aren't writing those pieces. I can't stress enough the importance of units. Units have two pieces, a measurement and a substance. You lose either of those pieces, it all goes to hell. Okay? I don't want you there. Write it down. Okay? So, let's be exciting. New concept, percent yield. Okay, we went through a whole bunch of stuff saying no formulas, no formulas, no formulas. Guess what? Here's your turn. Formula. The percent yield is the actual yield over the theoretical yield. Okay? Times 100%. And I always leave the 100% off and have to add it in later. Okay? What are the units on percent yield? Because I just said units, units, units. What are the units on percent yield? There are none. They disappear. Because when we go through to calculate a percent yield, whoa. We did the copper lab a couple weeks ago. We had the grams of copper that we obtained at the end. What did we divide it by? The beginning mass, which arguably you might say is the grams of ore. Well, those units don't cancel, Mike. That doesn't count. It does count. Because what are we assuming when we do that grams of ore? Our assumption is that that grams of ore could theoretically be all copper. Which means, what happens to the units? They cancel out. And you may be like, well, how would you know which is grams of copper actual, which is grams of copper theoretical? That's why we call them actual and theoretical. Okay? The actual is one that we actually obtained. This would be an experimental amount. We mass something out on the balance, there's a weight. What is the theoretical? Okay? That's going to change depending on what we're looking at. With the copper ore, our theoretical was a nice easy one to just mass out. Okay? We're still doing kind of a calculation. We're converting ore into how much it could possibly be in copper. Okay? We are making that conversion, but we've internalized that. Okay? What happens when we move to a chemical reaction, however, is that that theoretical now will have to be calculated. So when we look at a percent yield, it is oftentimes also referenced as actual over the calculated yield. Because almost always the theoretical yield is something you will have to calculate. How will you calculate it? Limiting reactants. You will take what you start with, run a bunch of calculations to say how much could this possibly have made. So you have to use that knowledge to determine a percent yield. If you don't have that knowledge, how do you determine a percent yield? You don't. Right? What units should you use for actual and theoretical? Okay? So in the case of grams per copper, the copper ore lab, it was grams of copper, grams of copper. We'll even use a different color to help accent that. What units did we use? Grams of copper. So the measurement unit was grams, the substance unit was copper. Should I always use the substance unit of copper? Why not? It depends on the, yes, I agree, the chemical equation. If the chemical equation doesn't result in copper, then it shouldn't be copper. Should it be grams? Maybe. Could I do it with moles? If I change that grams into moles, could I solve this for percent yield? Yeah, sure. What do you mean? We do have to adjust the theoretical, that is true. This would not result in a percent yield. This would. Why? What is the relationship between grams and moles for the same substance? For instance, for copper. If I was to turn the black grams into moles, how would I do it for copper? What would I need? The molar mass. The molar mass of what? Of copper. Cool. Let's convert the red grams of copper into moles of copper. What would I need? The molar mass. The molar mass of what? Copper. So to convert either one of those into grams or moles, I would need to multiply or divide by the exact same function. Which means it doesn't matter which unit I use as long as they're the same. All right? So we can use grams or moles. Typically, people want grams. Why would we typically use grams for a percent yield? Because our actual yield, how did we determine it? Not an actual yield. Through experiment. How do we measure our product in an experiment? Through a balance, which gets us grams. So almost always you see percent yield written in units of grams. It does not have to be in units of grams. It can be in units of moles. As long as the units you're using here are identical. The instant they are not identical, everything becomes wrong. Okay? So let's see. Cool. 2 moles of sodium carbonate are mixed with 2 moles of water and 1 mole of carbon dioxide. And only 0.5 moles of sodium hydrogen carbonate are produced. What is the percent yield of sodium hydrogen carbonate? What are we solving for? Percent yield, I completely agree. Okay, how do we solve for a percent yield? Actual over theoretical. Ethan, you're going to help me out? You called me out on it earlier. Actual over theoretical times 100. Okay. Am I given any of that information? Okay. The percent yield, this is the percent yield for what? Sodium hydrogen carbonate. Okay. Am I given any information about sodium hydrogen carbonate in the question? Yep, I'm told 0.5 moles. Again, we have that visual design issue that we have to stress about. Sodium hydrogen carbonate are produced. What does that mean? Actually obtained 0.5 moles. What did we theoretically obtain? Just like we said before, our theoretical is a calculated. We would have to solve for it. We'd have to solve for it based off of what? The balanced equation, converting each of the substances that I'm given across to product. Okay? How would we go through and convert sodium carbonate into product? And in particular, what type of product are we looking at? What is the unit we want for the sodium hydrogen carbonate? Why do you want moles? Perfect. The actual yield shows moles. Okay? What is our measurement unit going to be for our sodium carbonate? Why moles? I don't quite accept keep it easy, admittedly. Yes. We go back to the question, that's what was given. We were given 2 moles of sodium carbonate. Okay. We now know that I'm starting with moles. Okay. To keep it easy, I wrote the question to keep it easy, so we didn't have to worry about that. Is moles of sodium carbonate the same thing as moles of sodium hydrogen carbonate? No. Why? Different symbols. I'll accept that. 2 and H. Okay, so what do I need? A conversion factor. That conversion factor needs to do what? By converting, I need to place the sodium carbonate in the denominator. Why? To cancel the unit. What needs to show up top? Sodium hydrogen carbonate. What units should I use? What measurement unit? What measurement unit? Why moles? It's what I'm starting with over here. It's what I'm ending with there. I'm trying to do it as quickly as possible. Does that conversion factor exist? Where do I find the conversion factor to convert substances? A balanced chemical equation. What measurement unit is associated with the balanced chemical equation? Moles. Hallelujah, that's exactly what I want. So what do I got to do? 2, 1, and I would get 4. Should I put that 4 here? Why not? Okay. Was I only given sodium carbonate? No, I was also given water, okay, and a specific amount of water, not in excess of water. Every other question we've done in the past, it's been in excess. Why? Because we didn't want you to do limiting reagent calculation. We didn't want you to have to worry about it. We kept it simple first. We're now at the point where we have to make it more complicated and show you that more complicated. So what we'd have to do, 2 moles of H2O needs to become moles of our sodium hydrogen carbonate. What happens? Moles of H2O needs to cancel. Moles of sodium hydrogen carbonate needs to appear. What is that relationship? 2 to 1. How do you know that? Balanced chemical equation. There's a 4. Could move to our CO2, 1 mole. CO2 times yeah, I agree. Moles of CO2 need to be on the bottom. I think you started going with the top. That's cool. Moles of sodium hydrogen carbonate. Thank you for volunteering. It's been intense, so I appreciate that. Sodium hydrogen carbonate, number in front, 2, 1. Answer is 2 moles of sodium hydrogen carbonate. Which is my theoretical yield? 2 moles. Why is it the smallest number? Shouldn't my theoretical yield be the most I could make?
Yeah.
Wouldn't the most I could make be 4?
No,
Why not?
because you don't have enough materials.
Once I make 2, I no longer have CO2. Once I made 4 sandwiches, I no longer had bread. Right? CO2 is now my limiting reagent. It prevents me from continuing to react. I'm capped at 2, which means I can now put 2 moles of sodium hydrogen carbonate, and I almost forgot it, but I've got Ethan now sitting in the back of my head, so I appreciate that, times 100%, 0.5 divided by 2, and I get 25%. Do I need to show all of that work? As painful as it is, yes. Again, arguably, this would not be a show your work question because you could do each of those conversions, the limiting reactant conversions, in your head. At least some of you can. Okay? I will again caution you, if this was a multiple choice question, you should still write out the work because it'll be very easy to swap the location of the 1 and the 2 to change the end result. Question?
I really like you explain it, but I don't understand why you used the 2. Is it just because it was the smallest one?
So the easiest answer is just because it's the smallest one. Once I make 2, so all of these would make up to 2. Once I've made 2 moles of sodium hydrogen carbonate, how much CO2 is left over? None. Can I make any more? I'm literally out of CO2. I don't have those parts. Okay? I've run out of bread. I can't make any more. So when we're doing limiting reactant, calculate out for your final product. Whichever number is the smallest is your theoretical yield. Okay? It's the easiest way to just dump that in there. Okay? For those people that are still insisting that you can do it in your head, what is the percent yield?
There's no balanced chemical equation.
There was no balanced chemical equation given. Could you make one? Yes. You know what the reactants were. You even know what one of the products was. So you could try and write out the chemical equation. Be like, is this the proper chemical equation? Are you responsible for being able to look at pieces of a chemical equation and saying what type of chemical equation it is? Yes. Okay. Are you responsible for being able to predict the products of certain chemical equations? Yes. Guess which one of those equations this one is? One you're responsible for being able to predict the products for. This would be, which one is this? A neutralization reaction. You're responsible for being able to predict those products merely by looking at the reagents. Right? People are going to have a really hard time looking at the reagents to identify them because it's written in English. And English is a confusing as hell, sorry Greg, language. So what do we do as chemists? Screw English, let's write it in chemistry. When we write it in chemistry, now we can interpret. Now we can see those pieces that allow us to come up with the patterns to be able to say that we can come up with those. Okay? And Greg can easily counter, that's just a different writing system. Yeah.
You don't have to. You would
Okay.
write the way you would.
Okay? So we would have to do all that. To get you an idea before you start panicking, being like, is Mike really going to make me do this? I'm not going to make you do this one. Ultimately because as a group, I made a student in the Learning Center do it. It took him 45 minutes. It should not take 45 minutes. For somebody in 151, this is a question that you could expect multiple of on a single exam, okay, of 30 questions. Okay? So this has to become second nature. What are the pieces that you have to do? You have to be able to read magnesium hydroxide and come up with a chemical formula for those and for hydrochloric acid. How fast? Sub 5 seconds. Okay? What type of chemical reaction occurred? In the process of writing out those species, you should already have identified the type of chemical reaction and the products that are yielded. So in less than 10 seconds, you have a chemical equation. Right? Ooh, balanced chemical equation, already done. Maximum yield if hydrogen or magnesium hydroxide. Admittedly, balancing takes a little bit longer, so let's say 15 seconds. Okay? Maximum yield of magnesium hydroxide is the limiting reagent. This involves finding those conversion factors. How fast should those conversion factors come out? Okay? That one line right there, 30 seconds. We're up to 45 seconds total. Next one's another 30 seconds. Okay, we're up to, let's be nice because I can't add, a minute and a half. Okay, what's the real limiting reactant? Well, that was the smaller of those two. I'm not giving you any more time. That's a minute and a half. Your actual and theoretical yields, you just found the theoretical. The actual is reading in the question. Percent yields, dividing those two. In under 2 minutes, you've solved the entire question beginning to end. That's how fast this should be happening. Okay? That is intense. That comes with practice, and ultimately practice writing it down. Okay? I've been kind of watching this as we've been going through, and I fully admit, really intense. I kind of apologize, trying to tone back a little bit. But in all that yelling at the beginning, the suggestion was made that you should be writing down. How many of you have more than a page of notes? I said more than a page of notes. From today. Just the chemistry class. Okay? In the process of watching, it looks to me like the average amount of writing is less than half a page, if not less than a quarter of a page. We just spent an hour talking about how to solve questions, where to find information, and you've decided none of what I've said is important. You remember the whole feels bad? Okay. So when the exams come back and they're low scores, I tend to freak out a little bit. Okay. And then I freak out more when you aren't listening to what I'm having to say. Okay. Admittedly, all of these lectures are recorded. How many of you have gone back and watched more than one recorded lecture?
Not including play posits, those don't count.
Play posits are definitely not lectures. All the way through. Wow.
Or a clip from one, but
Okay.
that was nobody.
That means you've decided what I'm saying isn't important enough for you to write down. It's not important enough for you to review. Why are you showing up to class? I appreciate your showing up. It makes me feel somewhat good because there's people for me to talk to.
It's a stretch of an assumption, Mike.
Okay? It is. It is huge, but that's what I'm left with. Okay? Because I'm not left with anybody talking to me in office hours. Okay? I'm not left with anybody saying, hey, I can't make it to office hours. Can you come up with a different time? Okay? I don't have any of those tools to grab a hold of to say, you're trying to do something to work through this knowledge. Okay? I know it's hard. That's why I'm here. That is literally why you are paying me.
And when he asks, why are you coming to class? He's not saying, like, don't come to class. He's saying, if you're wanting to succeed, but you're not doing the things that are going to help you succeed, you want to think through your decisions, just like we've been saying all along. You want to think through those decisions that lead to success or lead to failure so that you can pick the ones that lead to success. For those of you who have gone back and looked at a few of his lectures, even if it was a 5 or 10 minute clip to review something, that's good. If you've only done it once or twice and you're still not taking any notes after 30 days of lecture time with us, 20 days of lecture time, you've logged a couple hundred hours with us face-to-face, or 90 hours face-to-face.
Sure.
Almost 100 hours face-to-face with us. For sure, that was important, except that you've logged thousands of hours other places too. So how much of that are you hanging on to? If you haven't been taking notes or you haven't been rolling back over stuff, all that's it's not going to stick the same way. And you may get recognition memory, like we talked about early on, but that doesn't mean you're going to be able to recall this on your own and be able to do it out of your head, or do it at least, or know the steps to take to solve something on paper. So you've got to be making those wise decisions and seeing them as a series of decisions, not just one. Do I show up to class today or not? That's one important decision, but there are 4 or 5 other ones.
Or acknowledging that you're okay with those consequences of barely passing the class or not passing the class. Okay? And I will admit, that's totally on me. I don't want you to just pass the class. And if that's your goal, we're going to have a conflict because I don't want you to just pass the class. You want me to, I don't want you to fail. I'm looking the other way. Okay? I want you at the very top of the class. That's where I want you to be. That's why I'm trying to provide you those tools, is to get you there. Okay? So if it feels like I'm beating you to try and get you up there and you don't want to get up there, I'm sorry, but that's not going to change. I want you at the top of the class. Okay? Because you absolutely deserve to be there. Okay? Knock it off. Okay, which gets us to the next kind of fun little part. Okay, empirical formula. So the first thing that I'm going to address right out of the gate with these, okay, is that this is an archaic system that I think is borderline not necessary for the sake of the course. Okay, to that end, what do you need to do for an empirical or a molecular formula? Literally in the slides, that's what you need to do, step by step. Okay? That's what needs to happen. Okay? There is bits and pieces missing in there. You'll notice it says grams to moles, and it just says molar mass. What does that mean? How do I convert grams to moles? I use the molar mass. Where do I find that information? Periodic table. So there's bits and pieces that are there to guide you along the way. It's not literally plug this into this, this into this. Okay? For the sake of this class, you will be seeing grams to moles. You will not be seeing the percent composition. Okay? Percent composition is a valid way to test it. You could use it. You could see it in homework questions if you decided to do those homework questions. Okay? What do you do with that? You assume you have a 100-gram sample. Okay? If you have a 100-gram sample, what do the percents become? They become the grams for whatever the element is, and you're back to A. Okay? Convert the grams into moles. Once you're into moles, we then need to divide all mole amounts, every single one of them that you came up with, by the smallest mole amount. Okay? And then round or multiply all values until you get whole numbers. Okay? Molecular formula, determine the molar mass of the empirical formula. Okay? Here's an empirical formula. Arguably this is a bad empirical formula, but we'll talk about it in a little bit. NaCl is an empirical formula. An empirical formula is the reduced ratio for a covalent compound. Is sodium chloride, as written, a reduced ratio? Yes. Why?
Because it's 1 to 1.
It's 1 to 1. I can't get any smaller than that. Okay? Is Na3000 Cl3000 still a valid formula?
Yes.
Yeah. Okay? We don't write that because that's confusing, and instead we do the reduced ratio. Okay? And we go all the way down to sodium chloride. And that's because in an ionic compound, they all link to each other. It is not, it's not a single bond from sodium to chloride. It's probably hundreds, or technically 4 different bonds outwards. okay, in the complex solid. I can grab any sodium in any nearby chloride and have a molecule of sodium chloride. Okay? Where it becomes problematic is back to the definition I said for our empirical formula. It is the smallest whole number ratio for a covalent compound. Is sodium chloride covalent? No, it's ionic. And we know that because we're pulling back hard stuff. Sodium is a metal. Metal, non-metal bond is ionic. Okay? So we wouldn't really refer to sodium chloride as an empirical formula. But if I look at the formula for benzene, C6H6, I could reference the empirical formula for that. What would its empirical formula be? CH. Is the empirical formula useful? Well, it does tell me the ratio of carbon to hydrogen. But when I reach in to grab a molecule of benzene, I'm not grabbing a single carbon and a single hydrogen. When I grab a single molecule of benzene, what am I grabbing? 6 carbons and 6 hydrogens that are all covalently linked to each other. Okay? Because there's a slightly different connection between them, I can now reference my empirical versus molecular formula. There are methods to determine the empirical formula independent of the molecular formula. We can then also use other methods to determine the molecular molar mass. Once I know the molecular molar mass, I can relate that to the empirical molar mass. Right? What would that relationship be, particularly for the case of benzene and its empirical formula? What do you think the difference is in the molar mass for the empirical formula versus the molecular formula?
6 times.
It would be 6 times. So the number will scale by 6. Once I've found that numerical relationship, all I have to do is multiply the empirical whole numbers by the number found in my division, and I would have my formula. Okay? So it's a process of moving through those pieces. We'll do one example. Right? An unknown sample was found to be composed of 24 grams of carbon and 2 grams of hydrogen by elemental analysis. What is the compound's empirical formula? What do we have to do? We have to find the molar mass. I'm trying to take 24.0 grams of carbon and convert it into moles of carbon. How do I do that? Molar mass from the periodic table. 12 grams of carbon is 1 mole of carbon. Okay. 2.0 grams of hydrogen. And I would get 2 moles. Which number is smaller, 2 or 2? They're the same, so it doesn't matter. Divide them both by 2. What do I get? 1, 1. My empirical formula is CH. Okay? 1 to each of them. Okay? If I hold that content, taking the exact same compound, but now I've added some more information. What is that more information I've added? The molecular mass. Now that I have the molecular mass, I could potentially come up with the compound's molecular formula. I know I have CH as my empirical mass. I have CX and HY for my molecular. Okay. The molecular mass is 78. What is the empirical mass? 13. How'd you get 13?
The 12 gram plus 1 gram.
The molar mass for carbon is 12. The molar mass for hydrogen is 1. Add those together. Why 1 of each? That's the ratio from our empirical formula. To go from 13 to 78, what do I have to do? Okay, I'll accept that. Take 78, divide it by 13, what do you get? I know, it's a multiple of 13, it's weird. It's 6. So what did I do to make 13 equal 78? multiply by 6. How can I make my empirical formula my molecular formula? Multiply by 6. My empirical or my molecular formula becomes C6H6. Interestingly enough, that happens to be benzene based off all the previous things. Okay? Okay, I know we're done. Just want to point out some review stuff. We've got the empirical and molecular rules again. Okay, review. I would recommend that you think about this and do this on your own time. What is the new content? What areas are you having troubles with? What areas are you super confident in? Then do you have specific questions? I do have office hours. Take advantage of those office hours, particularly for those specific questions. This will help you guide your studying process. Whoa, 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 whoa. This is my interpretation of new content. We've got dimensional analysis, which isn't new content. We've been doing that for a long time. We have the concept of a mole. Okay? We have the periodic table giving us grams per mole. Balanced equations giving us mole conversions, so substance conversions. Molarity giving us moles to volume. Gases, we have a mole to volume directly conversion. We have PV equals nRT. We have the limiting reactant reagent, percent yield, empirical formula, and molecular formula. All of those concepts are now new and will be tested on. Does that mean all of the old content will not be tested on? No. In fact, heavily you can bet the old content will be tested on. Okay? Because to do the new content, you need the old content. Okay? As soon as the exam is written, I will post to Canvas the breakdown of the exam, where content matches roughly and how many questions, so you can get a better feel of that. The exam is on Tuesday. We will be doing it next week. Okay, we will be doing it in the very first session, so we'll be starting at 11:30. I don't know why 11 always sticks in my head, but 11:30. You'll get the 75 minutes, and then we'll start into the English course again. Okay? Please ask questions. I do respond to email. You can take pictures and send me pictures of chemistry work. Just to clarify, that was a joke.